industrial effluent treatment plants, basically dairies, textile, cassava starch plant, which is a very difficult wastewater production factory. Cassava starch, they make glucose out of starch later. And confectionery, biscuits, soft drinks, they are in the business and diversified. So this is a 2400 KLD textile ETP. Again, three cardinal laws for a good ETP: proper design, engineering, operation maintenance, and the zeroth law we all saw. Just as in the STP, you need to select the appropriate treatment technology. In this particular case, it really means treatment train or the treatment system, whether it is anaerobic or aerobic, or it should be physical, chemical, or a combination of these. So this is the little bit of differentiation between STP and ETP. You have a wider choice of treatment units, which you have to selectively apply based on your experience, based on the particular wastewater. Please also keep in mind one very, very important aspect. Although we club all the organic pollutant matter into BOD and COD, the two BODs may not be the same. For instance, 100 milligram per liter BOD from a textile wastewater is not the same as 100 milligram per liter of BOD in a domestic sewage. Basically because the constituents, the components, the chemicals which contribute to the BOD are totally different. The matrix of the wastewater is totally different. And therefore, there are major differences. Although they say you may have 100 BOD in a textile effluent, or 100 BOD in sewage effluent, or 100 BOD in a dairy effluent, or a brewery effluent for that matter. All these are different. And therefore, you have to have a lot of experience understanding the difference between these industrial wastewater. So you cannot treat them on par. 100 BOD of textile is not the same as 100 BOD of a dairy. So you must have previous experience or knowledge of the wastewater, the characteristic of the wastewater, and how they behave to various treatment techniques. So this is the major difference in industrial wastewater treatment. The zeroth law in terms of ETP would be selection of the right treatment units. Type and size of the screen, for instance, whether you want to choose a manual screen, mechanical screen, the gap between the bars in the screen, the material of construction, all these are matters of design, matters of engineering as well. Oil and grease tap. The baffle channel based on EN 1825, there are very rigorous standards, European standards for designing an oil and grease trap. Whether you want to go for a tilted plate interceptor. A tilted plate interceptor is a beautiful mechanism for removing oil and grease. High concentrations of oil and grease can be removed with the tilted plate interceptor, TPI. And we have used this extensively in Bangladesh because, as I said, our client is in the foods business. And in the foods business, they do a lot of fried snacks and things like that. A lot of oil comes out in the wastewater. TPI or even maybe a dissolved air flotation would be a method of removing these oil and grease, free oil and grease. And whether you need to have a mechanized skimmer, an endless belt skimmer, which automatically remove the floated oil, or it can be a manual oil removal system. Again, it all depends on the quantum and quantity of oil and grease you expect to come out of the treatment plant. Then comes whether you need to have a preliminary treatment, even cooling, for instance. We designed a plant in Raipur. This was for a dyeing, yarn dyeing unit. Yarn dyeing is done in batch process in vats, big vats. And the yarn dyeing is carried out at very high temperatures of 80, 85 degrees centigrade. At the end of the dyeing process, the vat is discharged. The residual contents in the vat is discharged, carrying a little bit of residual dyes, as well as having high temperature. This high temperature is not directly, you cannot do anything in the EDP. You may have to go through a cooling tower before it comes into the main EDP. So even cooling is a good treatment unit, which can be used in an industrial effluent treatment plant. And of course, the equalization. Equalization, as I said, does two things. It buffers the peak flows. And in the case of industrial wastewater, it homogenizes the quality of the wastewater. Not only the quantity, but also the quality of the wastewater is buffered and made more homogeneous, and it is more or less a uniform characteristics or quality of the wastewater is what you want to you want the main ETP to see. So equalization tank in an industrial ETP does serves two purposes. One is it equalizes the flow, it equalizes the quality. Primary treatment, preliminary treatment, and then primary treatment. You have a number of options here again. Whether sedimentation, you make use of gravity, dissolved air flotation, DAF. In case the solids are not easily amenable to settling, you may try to float it out. And especially if it also contains oil and grease, DAF, dissolved air flotation, is the unit process of unit operation of choice. And chemical treatment, coagulation, chemical treatment, pH correction, all these fall under chemical treatment. So these are the primary treatment technologies, which are treatment units and facilities which are available. Secondary treatment, as I said, it can be anaerobic, it can be multi-stage aerobic, it can be single-stage aerobic treatment following anaerobic treatment or multi-stage treatment. And in the case of many of these industrial wastewater treatment plants, which especially in the food industry, where the BOD level, COD level are extremely high, we may have to necessarily go for an anaerobic stage followed by a two-stage aerobic stage to meet the ultimate BOD and COD standards. Typically in Bangladesh, of course, the BOD standards are fairly high. For industrial wastewater, it is 50 BOD and 200 for the COD. Only because if you go to Bangladesh, you see there is water everywhere. There is a river flowing anywhere you see. So plenty of water, and therefore the dilution factor or the capacity to take these loads, these pollution loads, is very, very high in the receiving streams. And that is one reason possibly the BOD level prescribed is higher, whereas in India, the BOD level prescribed is 10 milligram per liter. Tertiary treatment. These are preliminary, primary treatment, secondary treatment, and tertiary treatment. Tertiary treatment, you could have another stage of tertiary coagulation, for instance, then the normal pressure sand filter, activated carbon filter, disinfection. These are the typically recognized tertiary treatment schemes typically used. I'll give you a small example of a tertiary coagulation which we used in one of our treatment plants. We had a Brook Bond coffee factory, instant coffee factory making brew in Whitefield here about 30 years ago. 30 years ago, this Whitefield site was the Brook Bond coffee factory. Now it is converted to the Unilever Research Center, one of the leading research centers for Unilever across the world. The Brook Bond coffee factory, whatever the treatment we did, ultimately the final treated water still had a residual coffee color, the typical decoction color. Whatever you do, you could not remove it. Then I tried a lot of, in fact, that was 30 years ago. I myself used to come to the lab there and do the testing. So you have to do these trials and testing, the field trials, the lab testing on a small scale. I tried all the kinds of other like chlorine, which is supposed to be a good bleaching agent, for instance. So chlorine was the first thing which came to mind. But when we added chlorine, we found the color intensified. Actually, chlorine is supposed to be a good bleaching agent, but in fact, exactly the opposite happened. So there's nothing you can take for granted. So you have to do all these treatability studies when you're not familiar with a particular industrial wastewater which you have not done earlier, which you have not treated earlier. Treatability studies are a must. So this is the treatability studies we conducted. We tried many of these other coagulants as well, and finally settled on lime and alum or ferric chloride, which is the standard coagulants. And it worked extremely well. We could get rid of that residual color in treated water, and it still works. So tertiary coagulation, PSF, pressure sand filter, carbon filter, disinfection. And you could go for advanced tertiary treatment, where you want to go for further treatment using ultrafilter membranes, UF membranes, RO, electro deionization. When you want to get extremely low levels of TDS, you can go as low as 1 ppm, 1 milligram per liter, or 2 milligram per liter TDS, which are required in certain very complex industries. Electro deionization. And finally, evaporation. When you are left with RO, when you do RO and other things, you will have a lot of reject water, which are very high in TDS, which normally you will not be able to dispose of by other methods. You may have to go for evaporation. Typically, multiple effect evaporation is generally used, which is extremely energy efficient evaporation. And then, of course, after all this treatment leads to generation of excess sludge, biological sludge, chemical sludge. It could be primary chemical sludge, it could be secondary sludge, it could be even the tertiary sludge, as I said. All these sludges will also have to be handled, and you have again multiple technologies, techniques available for handling the sludge. If it is a small quantity, you can directly go for dewatering. If it is a large quantity, like in a very large plant, you will go for a thickening stage, a digestion stage, either aerobic, anaerobic digestion, conditioning with some chemical, maybe, and then finally dewatering. So all these different treatment technologies, treatment units, and facilities are available in the hands of a ETP designer. So it is your experience, your expertise to select the right mix of all these for that particular application which you have in hand, and to meet the quality standards specified for the treated wastewater. So you can see you need to have a lot of experience in handling that particular waste. And if you do not have previous experience, as I said, you will have to resort to treatability studies. And in fact, we are for some of the industrial wastewater treatment plants where we were not very familiar with the anaerobic treatment, we have conducted anaerobic treatability studies on small scale, on a bench scale, and then come up with the design criteria. So this is the diagram of a passive grease separator, that the BS and EN 1825, as I said. It consists of a sludge trap. This is a very simple separator. So there are very, very clear-cut, well-defined design criteria for the sludge trap, the dimensions, the length, breadth, depth, and everything is given in that standard. What happens when using AI to pull up images of a DAF unit? I wanted to show you a DAF unit, and I put up in Google, said show me an image of a DAF unit, and this is what I got in the first instance. And then later I got the correct DAF unit. This is the dissolved air flotation, where the influent you pressurize under high pressure. The treated water is mixed with air under high pressure, and then mixed with the influent and suddenly released at the bottom of this DAF unit. It is like your soda bottle. So a lot of fine bubbles are released when suddenly high pressurized water is released to the atmospheric pressure. Fine bubbles are produced. These fine bubbles lift up the finer solid particles as well as the oil and grease particles, and you get the floated sludge. This is the floated sludge, and there may be some heavy sludge particles, solid particles, which will also settle, and that will be the sediment. So in a DAF unit, you get two sludges out. One is the floated sludge out, the other is the sedimented sludge out. Both sludges you'll have to handle. Typical textile ETP. What is the design wastewater quantity? As I said, this was given by our client. He determines what is the design wastewater quantity, which he will in turn get from the supplier of the textile plant machineries, plant and machinery. The estimated quality of waste streams from the dyeing operations are also as follows. This also the client has to give from his process supplier. The pH varies, as I said, between 9.5 to 12. BOD 600, not very bad. BOD level seems to be under control. COD 1000 milligram per liter. So you can see the COD to BOD is hardly 1.7 to 1.8, and therefore readily, possibly easily biodegradable. The COD to BOD ratio is a measure of the biodegradability of the wastewater. Typically, domestic sewage, the COD to BOD ratio is 1.8. That is the standard we use for comparing biodegradability of other wastes in comparison. For instance, brewery wastewater, the COD to BOD ratio is 1.2 to 1.5. That means it is very, very, very readily biodegradable, much more biodegradable than domestic sewage. On the other hand, in a bulk drug industry, the COD to BOD ratio could be as high as 3:1 and 4:1 at the start in the raw waste. That means it is not easily biodegradable, or we call it refractory organics present. Refractory organics means not easily biodegradable. So here it is fairly easily biodegradable. So this is a good thing to know about the wastewater, the characteristics. You have to understand your wastewater very well before you can do any treatment or recommend any treatment methods. So understanding characterization of the wastewater solves 50% of your problem. You must understand your wastewater like the back of your hand. Then it becomes easy to put together the treatment scheme. Total suspended solids 150 milligram per liter. TDS, this is expected because they use a lot of chemicals, caustic acid and other things, so they will remain as TDS. So total dissolved solids comes to about 2000 milligram per liter. Oil and grease less than 20 milligram per liter. This is the design wastewater, raw wastewater. This is for an exfoliation plant. I don't want to go into this. Design wastewater quantity and quality. 340. Yeah. So this is the treated water quality for Bangladesh Department of Environment. As I said, BOD, although it was 50 milligram per liter, we will design typically for less than 50 milligram per liter. So in our design, we always take a value lower than what the government prescribes, or the Pollution Control Board or the Department of Energy, Department of Environment prescribes. COD prescribed was 250 milligram per liter, and therefore we will design it for less than 200. TSS is 50 milligram, that is okay. Oil and grease less than 10. And in the case of Bangladesh, because all these wastewaters are finally going to find its way directly into a river or water body, and fishery or fishing industry is a huge occupation in Bangladesh because of the presence of so many rivers and water bodies. Fisheries, fishing, pisciculture is a huge occupation for many of the Bangladeshis. And therefore, the Department of Environment is very strict on ensuring that the dissolved oxygen in the rivers or the water bodies doesn't get depleted because of discharge of wastewaters. And therefore, the dissolved oxygen which we let out from our campus after treatment should have more than 4.5 ppm of dissolved oxygen. This, I think, is a good parameter to introduce, which actually the Indian MOEF, Ministry of Environment, Forest, CPCB, will do well to follow. Introduce a dissolved oxygen requirement in treated domestic wastewater or industrial wastewater, because most of the wastewaters finally end up in lakes and rivers, where the flora and fauna can get affected if the dissolved oxygen, typically from a treatment plant, industrial wastewater or a domestic sewage treatment plant, will be in the region of only 2, 2.5 or 3 max by the time it reaches the water bodies. Treatment methodology. The treatment methodology selected for this particular textile industry wastewater was screening. We put a mechanical screen, in fact, because of the very large size of the treatment plant. Size also matters. Size and scale matter. If it had been a 100 KLD textile ETP, I would not have gone for a mechanical screening device. I will go for a manual screening, because there is an operator at site around the clock in any case. Equalization. This is an important thing. Equalization in a textile industry, you cannot have, or it is prudent to have an equalization which is done on a batch mode. By batch mode, I mean we have 2 equalization tanks, and therefore we run it in a fill and draw mode. When one equalization tank is filling, the other equalization tank is emptying, and therefore at the end of the equalization, you have one batch which has some uniform characteristics, which you can treat for chemical treatment, for the removal of color and other things. After doing the necessary lab studies, add the exact quantity of chemicals and other coagulants, exact pH correction, becomes the chemical treatment becomes much more simple, much more optimized when you do equalization in the batch mode for a textile industry. It is very interesting to watch a textile industry wastewater. If you sit at the ETP and watch it, every hour the wastewater color will keep on changing. In 1 hour it may be yellow in color, next hour it may turn black, green, red, depending on the dyes and other things which they discharge from the production department. And therefore, This kind of batch equalization is much better and more optimized for proper control of the treatment plant. Otherwise, it is extremely difficult because in continuous mode, you will not be able to dose the exact amount of chemicals to remove the color or remove the other particles and other things. And therefore, this batch treatment is the preferred mode. Fill and draw mode. Raw effluent lift pumps, pH correction, chemicals, and coagulation addition in the equalization tank itself. This is followed. This is the preliminary treatment stage. This is followed by a primary coagulation and sedimentation stage or clarification. We use a combination clariflocculator. Clariflocculator is a combination unit which has flocculation and clarification in the single combined unit. So this is the treatment methodology which we use. This is the treatment scheme or the flow sheet. Bar screen, equalization tank 1, equalization tank 2, and we add chemicals. When we are diverting the raw wastewater to equalization tank 1, it is filling. Equalization tank will be emptying, and when this is empty, this is ready for coming on stream. Equalization 1. This is how we operate in batch mode, fill and draw mode. Here, clariflocculator, we add the polymer in the flocculation chamber, followed by aeration tank. In aeration tank, because textile industry wastewater will be deficient in nitrogen and phosphorus, you will have to add supplement nitrogen and phosphorus by addition of urea and DAP. Urea contains nitrogen, DAP contains both nitrogen and phosphorus, and therefore you have to do a molecular weight calculations to determine how much of DAP to add, how many kilograms of DAP to add, how many kilograms of urea to add, based on the BOD to be removed. Typically in aerobic systems, the BOD to nitrogen to phosphorus ratio is 100 to 5:1. 500 kg of BOD you have to reduce. You have to add 5 kilogram of nitrogen and 1 kilogram of phosphorus. So you have to see what is the BOD removal in the aeration tank, because there is some removal in the primary sedimentation stage itself. Some BOD COD removal is removed because of the coagulation and settling. So the addition of urea and DAP, the nutrients, it will be based on the BOD arriving at the aeration tank and not in the raw wastewater. So these are all methods to optimize and reduce your operating costs. Chemical costs in textile effluent will be quite high because there is chemical required for pH correction, chemical required here for coagulation, polymer addition, urea and DAP. Quite a lot of chemicals are used in a textile industry wastewater. So this is the typical extendation plant. We again go for extendation only because we need to have a BOD less than 30 milligram per liter. So out of 600 milligram coming in the raw wastewater, about 25 to 30% will be removed in the primary stage. The balance will come to the aeration stage. Secondary clarifier, sludge settling, basically microbes into a sludge sump. We prefer to provide a sludge sump here and then pump it so that you can exactly control the amount of recirculation, not directly couple the pump to the suction of the pump to the clarifier bottom, the sludge line. Excess sludge will go to the sludge holding tank, and the primary clariflocculator sludge also comes to the sludge holding tank, and these sludges are handled in a centrifuge decanter here with addition of polymer. Polymer conditioning is definitely required when you have to use a decanter. These centrifuge decanter run at 3,000, 4,000 RPM. So centrifugal forces separate the water, the liquid and the solids. Polymer addition is required. Typically, polymer addition is 1 to 2% based on the dry solids which you want to remove, dewater in the decanter. And the decanted sludge cake, you have to further dry it, dispose it off. And since this sludge or this solid contains a lot of chemicals, it will be characterized as hazardous waste, and it will have to be disposed of under the category of hazardous waste disposal. It cannot be disposed of onto land and things like that. Either it is incinerated or into a landfill, proper scientifically designed landfill. There are authorized agencies for that. So this is a typical flow sheet of a textile, and it works extremely well. The treated water directly goes to a canal. Just outside the factory is a canal, which then meets the river. Treatment methodology, secondary biological treatment, single stage extendation, as I said, with aeration, mechanical secondary clarifier with sludge recirculation, sludge handling for chemical and biological sludge, we use the decanter centrifuge. Decanter centrifuges are rated depending on the quantity you can load it. 1 to 2 cubic meter per hour is the smaller centrifuge, then 3 to 4 or to 5 cubic meter per hour, the larger centrifuges. And there are very large centrifuges which can handle even 10 cubic meter per hour. So this particular unit used a centrifuge which would handle 6 cubic meter per hour. These centrifuges can run for 18, 20, 22 hours continuously. There's no need for that. So sludge handling is not a batch treatment. It is a continuous treatment. Treatment methodology, miscellaneous ancillaries, accessories, neutralizing chemical, as we said, is required because the wastewater can sometimes be acidic, sometimes alkaline. Neutralizing chemicals used, coagulants, lime, ferrous sulfate, or ferric chloride. Ferric chloride is one of the most versatile kind of coagulant which we use, and lime is a must because all these coagulants work well at a particular pH range. So lime is an adjunct chemical which has to be used. Lime itself is a good coagulant, in fact. Polymeric flocculant should be used, air blowers, nutrients for biological stage, polymer for sludge conditioning and dewatering, pumps, piping, electricals, instrumentation. So these are some of the other ancillaries and accessories and adjuncts which you need apart from the treatment units themselves. So that an ETP is a whole. Now select the treatment units, equalization cum neutralization tank, fill and draw type, as we said. In view of the varying nature and quality of wastewater from time to time, depending on the type of dyes being used, it is prudent to construct the equalization tank in 2 separate compartments to enable good control over pH and addition of coagulant chemicals, exact dosage of chemicals so that you get the required level of treatment. If it is a continuous process, it will be extremely difficult to continuously change the dosages. It is extremely difficult. We know of no automatic methods to control these dosages in the case of when you want to remove color, the dyes, and other chemicals. So this is the design criteria which we used. Design flow capacity 600 cubic meter per compartment. Each equalization tank compartment 600 cubic meter. So you have 4 batches of equalization, 1 batch of 6 hours flow, 4 batches in a day. Number of compartments 2. Retention time 6 hours, the dimensions, aeration mixing, because it contains a lot of solids, you have to homogenize it, you have to provide aeration and mixing so that homogenization takes place. That is the purpose of the equalization tank. You have to homogenize the effluent. Air quantity depending again on the size of the unit. Since it is for depending on the volume, capacity, and based on your experience, you will design what should be the air requirement. Typically, 1 cubic meter per hour of air is sufficient for 1 cubic meter of equalization tank capacity. Again, it depends on depth of the tank and so many other factors as well. And the floor coverage of the diffusers which supply air. So it requires a little bit of experience, previous experience or knowledge of these matters before you can. As a thumb rule, yes, 1 cubic meter of our air per cubic meter of the tank volume. But that is not a hard and fast rule. Select treatment unit. Utilization tanks are operated in batch, fill and draw mode. 1 compartment, as I said, optimal dosage chemicals. For pH correction, coagulant addition, equalization tank is suitable. We don't do it online. Next is the clariflocculator. Clariflocculator is the next unit in the treatment scheme. Combination unit, a central circular compartment which acts as a flocculator. Typically 20 to 30 minutes is the retention time or the flocculation time. Flocculator compartment is provided with a slow speed paddle flocculator, so that the smaller particles, solid particles, coalesce together, hit against each other, coalesce into larger size particles, and are easy to separate out, easy to settle out, and typically with the addition of long chain polymeric polymer. In order to accelerate for flocculation and color removal, a cationic polymer may be dosed into the flocculator compartment. Typical dosage of polymers 3 to 4 ppm only. And approximately 10 kilogram of polymer per day was used in this 2400 KLD plant. Typically, the polymer being an extremely viscous solution, the polymer becomes extremely viscous when you add water. You have to prepare a 0.1 to 0.25% solution. Or approximately, if you want to make 10 kilogram, you have to have a 4,000 liters tank, 4,000, 5,000 liter tank to prepare this solution. This is extremely viscous, and therefore you have to control the viscosity so that the pumps and other things perform properly. The dosing pumps for these coagulants. Throughput flow, overflow rate. This is the design parameter, design criteria for the clariflocculator. Overflow rate, that is the upflow rate or the upflow velocity in the clariflocculator, is 24 cubic meter per square meter per hour. Or in other words, simply put, it is 24 meter per hour is the upflow rate. Superficial area, therefore 100 square meter, and I come with the dimensions of the clariflocculator, 11 meter dia. And minimum side water depth prescribed for all these settling or sedimentation units is 3.5 meters, 3 to 3.5 meters. I prefer a larger depth to get a thicker sludge out. The thicker the sludge, easier to dewater, to handle the sludge and dewater the sludge. So typically, if the situation permits, I would go for a 3.5 meter water depth in these settling tanks and clarifiers. Tank volume comes to 385, 3 hours retention time, perfect within the prescribed thing. Minimum retention time required is 2 hours and more. Flocculator compartment, as I said, we need about 20 to 30 minutes. So I selected the flocculator compartment, 4.4 meter dia, flocculator depth 2.5 meter, a little less than the total depth. The flocculator volume comes to about 38 cubic meter, and therefore retention time 23 meters within the permitted range of 20 to 30 meters. So this is how we selected the clariflocculator. A typical clariflocculator looks like this. You see the central compartment. This is the flocculator compartment, and you could see the flocculator paddles. So these are driven by separate motors and gearboxes attached or placed on the bridge. This is the rotating bridge. This is a single arm bridge. In other cases, you could have a complete bridge across the diameter, but then it becomes a little more this thing. And this is the clarifier compartment. The external annular outside compartment is the clarifier. So the feed comes in maybe from the side, enters the flocculator, the flocculation compartment, then the solids settle down. The solids settle down in the central hopper from where it is taken out, and the clear water comes out and goes over this launder. So this is how the separation takes place. The solids separate out, settle at the bottom, and are taken out by the taken out into the sludge sump. There's a buried pipeline. The sludge line is buried below this floor of the clarifier, gets into the sludge holding tank. So this is a typical clariflocculator. Rotating bridge, you can see this is driven again by a motor and a gearbox, and it can either go run on the wall, the launder wall, or you could provide a rail, for instance. A rail is also used, typically like in a railway line, rail track. This is the decanter centrifuge which we used, Aldec 20, alpha level, 4 to 5 cubic meter per hour is the capacity. This is the alpha level decanter centrifuge. Very, very compact, very effective, very good machine. And this is the aerial view, if you can see, of the 2400 KLD textile ETP. These are the equalization tanks here, the 2 equalization tanks where all the chemical dosing, everything takes place. This is the clariflocculator. From the clariflocculator, it goes to the aeration tank. From the aeration tank, it comes to the secondary clarifier and out. From the secondary clarifier, there will be a sludge sump, which then recycles the sludge back to the aeration tank. Very, very simple, straightforward, and excellent quality of water we get. And this treated water, you will see, I'm not sure what this is. This is the trickling filter. Just show it for this thing. Yeah. So that is about the textile industry wastewater treatment plant. Excellent quality we get. I don't have the thing there, but it should be somewhere here. Yeah. Any questions on this textile wastewater? I'll show you some of the figures here. Any questions on textile wastewater?
Sir, normally they will say that there are a lot of salts that are coming out by the dyeing process, sodium salts of various kinds.
Yeah.
Um, I mean, where do you actually remove all those sodium salts? Uh, is it in the preliminary or the, I'm sorry, primary or the first step, or the pre-treatment step?
No,
Is it?
uh, sorry, I think my Microsoft Teams is not responding. Can you hear me?
Yeah, we can hear you, sir.
The sodium salts and other things cannot be removed in any of the treatment plants here, treatment units which we have used here.
Okay.
In fact, only the TDS will increase because of the addition of these other chemicals. TDS, if you have to remove, you have to go for some kind of a demineralization unit, uh, like DM plant or RO plant. Only then you can control the TDS. But fortunately, in this particular case, TDS level was less than 2000, and therefore was not a major issue.
No, because most of us who work as on an academic level, most of the time, whenever we do work, they say how. Let's suppose we are looking at activated carbon for the removal of the dye, and it actually affects the amount that gets absorbed, the presence of the sodium salts, even if it is in a less scale. So, would you recommend that we use the deionizer before or after the activated carbon column? Sir, can you hear us?
Yeah, I think Dr. Lima, you have to give me
Yeah, yeah, I'll give you permission.
permission.
Yeah.
Yeah, thank you.
So when we're working with real effluents, is it advisable to use it after the activated carbon column or prior to that, the deionization step?
Deionization only after carbon, because whatever can be removed by your biological treatment, chemical treatment, you have to remove, because removing anything using these membrane technologies is going to be very, very expensive. So the best thing is to remove as much of pollutants as possible using the conventional technologies, and only then go for UF or RO for removing those final. So it will be like a polishing unit only. You cannot overload this. UFRO cannot be the main treatment units. Just as in even in the case of, let us say, the tertiary units, sand filter, carbon filter, you cannot use them as the main treatment units. These are also considered as final polishing units. The bulk of the treatment should happen prior to these tertiary treatment units, either in the primary treatment or secondary treatment. So that is the concept any environmental engineer must have. Use technologies which will do the treatment most optimally and at least cost. So biological treatment is the least cost method. Next is the physical chemical treatment, and finally the tertiary treatment and advanced tertiary treatment. So you must select these treatment units only in this sequence. Use all the technologies which are conventional, which are cost effective, which are optimal, and then go to the other technology. Are you able to see this presentation, ETP?
Yes, sir.
Okay.
Your industrial ETP.
Industrial, yeah.
Yeah.
So these are some of the industrial treatment plants, as I said. And let me go to the Bangladesh plant. This is Toyota Technopark, major upgradation ETP Britannia. This is for a dairy UTP. Fabric. This is again for Bangladesh only. As I said, 2400 KLD, 600 milligram. This is the exact case study we talked about. We were to be compliant as per the Bangladesh Department of Environment. No environmental impact, appropriate addition of nutrients to supplement nitrogen and phosphorus. And you can see this is the Habiganj Industrial Park of this thing. And the final treated water. In this Habiganj Industrial Park, we have set up about 5 different ETPs. As I said, for a foods plant, for a textile plant, for a cassava starch plant. There are 4 or 5 different treatment plants. All the treated water is collected in a huge lake here, a lake receiving treated water from all Ecotech ETPs. And here, actually, we grow fish. Pisciculture is followed. This is the quality of water we get from this. So it is fully compliant. So automatic controls, even there is a nickel electroplating wastewater as well in this industrial park, where we remove nickel, zinc, iron, phosphate, chromium with ammoniacal nitrogen. Automatic controls for pH and oxidation reduction potential in the ETP. And this is the quality of water. We use this is used in pisciculture, in fact. So just wanted to show you that. This is another mango pulping unit, again for Bangladesh, in Rajshahi. Rajshahi is one of the mango, and this is what we said, the textile ETP. And this is the testimonial. Okay, that completes the presentation on the textile wastewater.
Anand sir.
Yeah.
Which type of polymer you used in last 2 or third last slide? You have mentioned some polymers.
This is for sludge dewatering. We prefer the cationic polymer. GE makes a good polymer. I'm not able to get the name directly. Many manufacturers have these polymer. Again, there are anionic polymers, non-anionic polymers, and cationic polymers. Typically for settling and dewatering more or less of the same category of solid liquid separation. Basically, they separate solid and liquid, whether it is plain sedimentation settling or it is dewatering using a centrifuge and things like that. The unit process is still solid liquid separation, and cationic polymers are best suited for this.
Is it resin based polymer, sir?
Yeah, it is. I don't really recall what this thing is.
पर आपका हो गया था फिर अगर नहीं सुननी है.
Okay, thank you, Anand sir. I will ask you on later.
Yeah, I will get the detail. In fact, we have that name of that polymer also. I will share with you the material data sheet for that.
Definitely, sir. We will discuss on later on this part.
Sure. So let me go to the next one.
Yes, sir. One more question, sir.
Yeah, sure.
Sir, actually, in the electroplating industry, did you use electrolysis process or some other process?
No, it is chemical treatment only, not electrolysis.
Okay.
Different elements, different treatment. For chromium treatment, we do that bisulfate, reduce the hexavalent chromium to trivalent chromium, and then settle it at high pH as a chromium hydroxide. Cyanide was separately treated and then mixed. So different treatment. Nickel is straight away nickel, depending on the solubility curves, you can basically precipitation at different pHs.
Okay, sir. So in the sulfate, I think you have used sodium sulfate.
Sodium bisulfite is what is the reducing agent we use.
Okay, sir. So, sir, what is the concentration limit of persulfate? Because if you use sodium sulfate or such type of salt, then there is a generation of persulfate sodium. Then
No. Okay. The bisulfite directly goes to reduce the chromium, and then it will be in the chromium, hexavalent chromium becomes trivalent chromium, and when you remove it, you use the exact, you have to do the treatability study again and determine what will be the dosages required to do. And we carry it out at 2 to 3 pH. At low pH, we do the reduction of the hexavalent chromium. we have not found any persulfate or anything in the treated water. As long as you use the correct dosages, there is no harm. Only if you start doing excess treatment, then you will have all these problems. The same as urea and DAP. You must use the exact amount of urea and DAP calculated based on the BOD you want to remove. If you use excess, you will be losing chemical, you will be adding nitrogen and phosphorus in that wastewater which you discharge.
Okay. So, sir, there is no generation of persulfate. You can
No, absolutely not. No, that's what I say. These are all, you can start with some thumb rules, but then you have to specifically tailor your treatment technology and treatment SOP, standard operating procedures for your specific treatment plant.
Okay, sir. Or is there any, sir, sulfate radical generation during the process or not?
No, nothing.
Okay. Thank you, sir.
Anand sir.
Yeah.
As I said, Dr. Vinod, there is a chance to generate persulfate, I think. Then what we have to do?
I have no idea, sir, because we have not come across, but certainly.
Okay. Thank you, sir.
We'll certainly look into it.
Yes, sir. Because during the process, there is a possibility of generation of persulfate ions also, or sulfate radicals. So that is why I was asking that is there any certain limit or of these generations, or have how we can control the concentration of persulfate or sulfate radical generation during the process?
Okay, we'll check that in our Bangladesh plant. Our person keeps going there to commission many of these treatment plants. So the next time he goes there, we'll certainly look into that and see what is the level of persulfate, and if there any, we'll have to find out some means of
yes, sir, definitely.
Yes, sir. Yeah, can you see the screen? Biological nutrient removal.
Yes, sir.
Yeah, this is recently, although it's a general presentation, we did a presentation to the Phoenix malls. Phoenix mall we have recently introduced the denitrification stage. Earlier it was not required. Almost all of the STPs across India do not have a denitrification stage as yet. But all the new plants which we started designing about 6 months ago, we have introduced a denitrification stage, an anoxic stage following the modified Lutsak-Ettinger process for denitrification. And all the existing STPs which do not have this facility, we are now retrofitting a denitrification stage. So this is how we do it. And it is extremely difficult. If you see, many of the STPs in residential, commercial complexes, in fact, in this mall itself, are in the basement. Space is limited, space constraint is there. So we have to find ways and means of introducing this retrofitting a denitrification stage. So this is one of the method. This is what we use. The technology used is the MLE process. So this is the NGT order dated 30th April 2019, quashing the MOE of October 2017 notification. In October 2017, the Ministry of Environment and Forests removed all requirements of nitrogen and phosphorus control. In 2015, in April of 2015, MOEF and CPCB introduced nitrogen and phosphorus control, but in 2017, they retracted it and said no need for nitrogen and phosphorus control. And some people went to the NGT as a public interest litigation. And this is the NGT order of 2019, which reintroduced these limits for total phosphorus and nitrogen. Total nitrogen has to be less than 10, ammoniacal nitrogen less than 5, and total phosphorus now, in fact, the NGT says less than 1 ppm. Although no pollution control board has now implemented phosphorus control, in Karnataka, the KSPCB has already introduced total nitrogen and ammoniacal nitrogen control. Maharashtra is the next state which has introduced this. So all our treatment plants in Maharashtra and Karnataka, we are going to do nitrogen control. In all new plants, we have already designed for denitrification. Similarly, again, even in Chennai, we will be shortly doing the denitrification for the Phoenix mall. So this is the background for nitrogen phosphorus control. The contents of this presentation: nitrogen, forms of nitrogen and definitions, the nitrogen cycle in the environment, reactions and conditions for these nitrification, denitrification stages, and the moral of the story, denitrification strategies. And let me again reiterate, these denitrification, this presentation is purely focused on these small scale, decentralized urban STPs. So different criteria, different concepts may be used for large scale treatment plants, like municipal treatment plants. We are talking about these small scale plants. What is the most optimum strategy and technologies to be used? Phosphorus, P removal, chemical, biological removal stages, chemical usage. What are the chemicals which are typically used? The conditions for usage of these chemicals. Biological phosphorus removal later for large STPs only. We will not get into that right now. But large STPs will have to go for biological because the chemical costs become very high. 3 cardinal rules for a good wastewater treatment plant, as you already saw. We'll not get into that. And these are the different appropriate technologies for the different size of the STPs. Micro STPs, ANBR, mini externalization, small externalization, large MBBR and SBR, and future MBR. The zeroth law, of course, they choose the right treatment technology. Nitrogen. What are the forms of nitrogen in domestic sewage? Total nitrogen typically 25 to 30 milligram per liter. Total nitrogen consists of total gel-down nitrogen, TKN, plus NO2 plus NO3, nitrate and nitrate. Total gel-down nitrogen in turn is defined as the concentration of ammonia, ammoniacal nitrogen, plus organic nitrogen. Ammoniacal nitrogen is NH4N, but I will use this interchangeably, NH3 and NH4N. Typically, it will be in the form of NH4N, ammoniacal nitrogen. Organic nitrogen consists of the amino acids, the proteins, example, urea and uric acid, typically from human discharges in urine and so forth, from the toilets. Nitrite, NO2, NO3, nitrate, nitrogen gas. Refractory nitrogen, not biodegradable. Nitrogen is an unwanted nutrient in water bodies like lakes and causes eutrophication, as we all know, or growth of weeds, uncontrolled growth of vegetation, destroying these water bodies. And that is the reason nitrogen has to be controlled when you discharge it into a river or a lake or a water body. This is the primary requirement. Forms of nitrogen, 3 stages in the nitrogen removal cycle. Ammonification. As we all know, in raw sewage, it is all in the form of organic nitrogen and ammonia. Uric acid. So this has to be first converted to ammonia. Ammonification is the first stage for in the nitrogen cycle. Next, all of this ammonia has to be oxidized to nitrate. This is the nitrification stage. And once all the forms of nitrogen in the sewage are in nitrate form, typically a vast majority, 95% will be in nitrate form, very little in ammonia form and nitrate form, very little nitrate in fact. All of it is in NO3 form, and then the denitrification. You have to remove this nitrate and separate the nitrogen and the oxygen, release nitrogen gas. That is the denitrification stage. So in a domestic STP, all these stages are encountered. Ammonification, nitrification, denitrification, and then you are done. You control both the ammoniacal nitrogen to less than 5 ppm and the total nitrogen to less than 10 ppm. Again, there are various differences. You have to be aware that the 25 to 30 milligram per liter total nitrogen we said earlier may apply in a typical residential complex. In a residential complexes, there are a lot of other dilution waters, like from the washrooms, the bathing, the showers and other things, which may not be the case in the case of an IT park or a commercial complex where such dilution may not be available. And here the nitrogen content may go as high as 40, 50 ppm. So you have to be aware of all these differences which can occur, which you can encounter in the raw sewage. So thumb rule, yes, domestic sewage, it says 25 to 30, but then you have to take it with a pinch of salt, apply your common sense, some logic, and see whether it is applied in the commercial scale. It may be totally different. In fact, we have witnessed this in one of our treatment plants. It goes as high as 60 milligram per liter, and therefore we had to do a special study to see how to control the nitrogen to less than 10 ppm. So we have to be careful. We have to characterize the wastewater extremely well before we do apply any of these denitrification strategies. The first reaction, as I said, ammonification, organic nitrogen, urea and fecal matter is converted to ammonia by hydrolysis. It happens very, very automatically. Hydrolysis in the presence of water, all this urea gets converted to ammonium ion. Urea plus water plus hydrogen ions, ammonium ions plus carbon dioxide. Here, ammonium ion and NH3 I'm using interchangeably, ammonium ion. Next in the nitrogen cycle is the nitrification. Basically an oxidation process. Ammonia gets converted to nitrate. This is a two-stage process, two-stage rapid process. First, ammonia gets converted to nitrate, the first oxidation intermediate. This is done by a bug or a microbe called Nitrosomonas. Next, nitrite gets converted to nitrate by another set of bacteria called Nitrobacter. And the second reaction is extremely fast, and therefore you will not have too much of nitrite present in the wastewater at any point of time. Again, depending on the environmental temperature and other conditions. At very low temperatures, in fact, the second reaction becomes slower, and therefore there is a risk of nitrite remaining in the wastewater. Fortunately, in India, we don't face such low temperatures like 5 degrees, 10 degrees, where nitrite could become a major issue. These are all chemotrophic bacteria. Nitrosomonas, Nitrobacter, chemotrophic bacteria, that is, bacteria get their energy from oxidizing inorganic compounds. They oxidize these inorganic compounds and therefore they get their energy from there. Nitrification, so ammonia in raw sewage, because it is presented as ammonia because of ready hydrolysis, and then the nitrification in the aeration stage. What are the favorable conditions for nitrification? Nitrifiers are strict aerobes, and therefore you need free dissolved oxygen in the wastewater. Dissolved oxygen level should be more than 1 milligram per liter, 1 ppm. And in all our aeration systems, biological aeration systems, we maintain 1.5 to 2 ppm, and therefore it's not a major issue. And in fact, in MBBR technology, as you saw, you are maintaining 3 to 4 ppm dissolved oxygen. Again, not a major issue. So nitrification happens very, very easily. Long retention time is required, low food to microorganism ratio. All these is met, as I said, in our recommended extended aeration system. We have long retention time, we have low F by M, high MCRT, mean cell residence time, which is equivalent to sludge age. As I said, we have 20-25 days of sludge age. So all conditions favorable for nitrification are available in an extended aeration plant. Adequate alkalinity for buffering 50 to 100 milligram per liter. Typically, we will have these kind of alkalinity levels already present in domestic sewage. You may not have to externally supplement by adding any alkaline agent. pH between 7.5 to 8.5. Temperature also plays a major role in nitrification. For every kg of ammonia oxidized to nitrate, 4.18 kg of oxygen is consumed, and similarly 7.14 kg of alkalinity is also used up. And that is the reason we need sufficient alkalinity in the wastewater. pH versus nitrification rate, this is the typical curve. And as you said, 8 to 8.5, 7.5, 8, we operate in this range. So you get maximum nitrification almost beyond, above 95% nitrification happens in a typical biological aeration system, especially the extended aeration system. Once you have nitrified all the forms of nitrogen to nitrate form, next is the denitrification stage. Nitrate must be removed from the system, and this is done by liberating nitrogen gas under carefully controlled conditions. We use heterotrophic facultative bugs, microbes. Heterotrophic meaning they need carbon as a source of food. Facultative means they can take oxygen either from dissolved oxygen in the wastewater or from the oxygen present in the nitrate. So we have to maintain the conditions in the denitrification stage so that these bacteria selectively utilize oxygen from the nitrate.
ये कर लो ऊपर वाला हाँ अर्थ एक्सप्लोरर लॉगिन कहाँ से करो अर्थ एक्सप्लोरर लिखो इसकी जगह यूएसजीएस की कंपनी का नाम है अच्छा इसके अंदर अर्थ एक्सप्लोरर
So you have to maintain certain conditions in the anoxic tank that the facultative bugs selectively take up the oxygen from the nitrate and release nitrogen gas. Hence the anoxic conditions. Anoxic conditions meaning very, very low dissolved oxygen at 0.2 to 0.5 ppm, so that these denitrifying bacteria will selectively use oxygen from the nitrate for oxidation, and they will use the BOD and COD coming in from the raw sewage itself as food. So we can force the bacteria to take up oxygen from the nitrate and reduce it to nitrogen gas. NO3 goes to N2O and N2. This is again a two-stage reaction. So the final reaction is nitrate in the presence of pollutants, the bacteria or the food liberates nitrogen gas, and water and alkalinity is released. Optimal pH 7 to 8.5 alkalinity produced, and therefore this alkalinity produced is 3 to 3.6 kilogram per kilogram of nitrate removed. And therefore you can see during the nitrification stage there is consumption of alkalinity. During the denitrification stage there is a release, or the alkalinity is put back into the wastewater, and that is the reason why we don't need such high levels of alkalinity present in the wastewater. If both DO and nitrate are present, the facultative bugs will preferentially go after DO first, and denitrification may not occur. So you have to be careful of the ensuring that the low DO conditions are met. And that is why we prefer in all the denitrification plants, we recommend introducing a DO sensor so that DO can be carefully maintained to be less than 0.5 ppm. Moral of the story in summary, we cannot denitrify unless we first nitrify the ammonia nitrogen, and we need the aerobic treatment for this. Anaerobic treatment will not do it. In fact, if you go for the anaerobic route, the ammonia will remain as ammonia, and you will have to use some other technology like to remove ammonia. Breakpoint chlorination, for instance. Breakpoint chlorination is another method for removing ammonia. You use excess chlorine and then remove the ammonia. So if you go for an anaerobic treatment route, for instance, the DWATS technology we were talking about, the ANBR, the anaerobic baffle reactor technology, the only way to remove ammonia in that particular treatment scheme is by breakpoint chlorination. We cannot denitrify unless we nitrify the ammonia to nitrogen nitrate. Organic nitrogen must be converted to ammonia through hydrolysis to be nitrified. Therefore, denitrification calls for both aerobic and anoxic stages for treatment. So urea fecal matter in sewage gets, by hydrolysis, gets converted to ammoniacal form. Ammoniacal form, this is the nitrification reaction. Nitrification reaction in the aerobic aeration tank. First nitrate, this is the nitrosomonas. Next nitrate, this is by nitrobacter. And then this nitrate gets converted. In the denitrification state, it gets reversed. First you form NO2, then nitric oxide, nitrous oxide, and then release of nitrogen gas. This is the denitrification stage. So denitrification schemes in a treatment plant, there are various methods for denitrification. One is the pre-denitrification, the modified Rutsack-Ettinger process. There is something called post-denitrification, that is after the aeration stage you can do denitrification, or there is a very complicated 4 and 5 stage Barden-4 process developed by Dr. Paul Barnard, a Vanderbilt University alumnus, and there are some other very, very complicated AO, A2O process, etc. for denitrification. These are typically maybe useful on a large municipal scale, but in a small scale, we will go only for one of these two, pre-denitrification or post-denitrification. And we prefer pre-denitrification because this becomes totally independent of operator intervention. Once we design the pre-denitrification stage, set the recycle rate, the mixed liquor recycle rate, there is nothing the operator has to do. Whereas in post-denitrification, it is more operator dependent. It depends on how much of additional chemical he has to use and things like that. So it becomes more operator intensive. We don't prefer that. We want to keep a treatment plant as simple as possible without any operator error. So we recommend the pre-denitrification MLE treatment scheme. Presentation, there's a detailed presentation on all these things from the Michigan Department of Environment, which I do go through for the MTech course, but here we'll not go into that. It's a separate 1-2 hour session by itself. As I said, caution on anaerobic plants. Anaerobic dewarts can be attractive in terms of low manpower in these micro STPs, but it's a huge tail risk for denitrification, as the only alternative chemical alternative is breakpoint chlorination, which will result in tremendous chemical consumption and OPEX costs. So these anaerobic plants now, the dewart system, the ANBR system, we now limit it to 30 to 40 KLD only. Beyond that, it is not economical. We go for the conventional aerobic systems, but we will design the aerobic system for 12-hour operation, maybe, not 24/7 operation. So these are some of the denitrification schemes, typically, which we see. This is the pre-denitrification, the mixed, the modified Lutz-Ackertinger process, where the raw sewage comes into the anoxic chamber, anoxic reactor. From the anoxic reactor, it goes to the aerobic reactor. And before the wastewater enters the secondary settling tank, we capture the mixed liquor here, because all this now is converted to nitrate. All forms of nitrogen here in the aerobic reactor are in nitrate form, and this nitrate rich wastewater is recycled back. This the mixed liquor recycled back to the anoxic tank. And also the standard recycled activated sludge. RAS sludge from the settling tank also comes to the anoxic reactor. So the anoxic reactor has a mix of all these kind of bacteria. The carbon-eating bacteria, the nitrifying bacteria, the denitrifying bacteria, nitrosomonas, nitrobacter, all of them are present. Here in this anoxic reactor, we now maintain a low dissolved oxygen regime, so that the denitrifying bacteria use the oxygen from the nitrate recycled back here and liberate nitrogen gas. And for food, they have enough BOD coming in from the raw sewage. So it's a very simple process. Once you set the recycle rate, it runs by itself, automatic. And then your treated water, and depending on the amount of nitrogen incoming, you can determine by a mass balance, a nitrate balance. You do a nitrate balance and determine what should be the recycle rate. Whether it should be, if influent rate is Q, whether the mixed liquor recirculation rate should be Q or 1.5 Q, 2 Q, 2.5 Q, or whatever, has to be determined by a nitrate balance around this aerobic reactor. We do a control volume. We select a control volume around this and do a nitrate balance, and then determine what should be the recycle rate, MLR recycle rate. And in fact, in one of our treatment plants, where the incoming nitrogen level was coming to almost 80 milligram per liter, we had to use a 4Q recycle rate. And 4Q recycle rate, as you all know, in an MBR, it was an MBR system, in fact, MBR STP, 4Q is the normal recycle rate. So we didn't have to bother much about excess energy consumption. The MBR technology itself is amenable or excellent, well suited for denitrification, because even without denitrification, it calls for 4Q recycle. So we are not expending extra energy just because of the denitrification stage. The other most commonly used denitrification strategy in small scale STPs is the post denitrification here. Here the influent aerobic reactor, all forms of nitrogen gets converted to nitrate here, and then comes the anoxic reactor. Now we have a problem. We may not have enough organic matter for the bacteria to use as food, and therefore we have to supplement BOD or organic matter by addition of methanol. So methanol addition becomes an additional treatment requirement for if you do post denitrification. And this is the only thing we want to avoid, but otherwise it's a fairly straightforward thing, only becomes more operator dependent. And you remove the nitrate, again nitrogen is released by the denitrifying bacteria. This is the complicated Barden-4 process. You have an anoxic reactor, aerobic reactor, MLR, mixed liquor recycle, then followed by an anoxic reactor, and then a re-aeration stage here. In fact, it is missed out here. You have to do re-aeration here and then the secondary settling. So it's very complicated, but we have done one Barden-Foe design for Jindal Steel in Bellary. They wanted a nitrogen level of less than 1 ppm in the effluent. In which case, these technologies, these techniques may not be the best suited. We went for the Barden-Foe process, a 5-stage Barden-Foe process, where it was a 3 MLD plant. So depending on the size of the plant and the requirement of the treated water, you have to select the best technique or technology available, strategy again. Again, the same thing applies. Depending very specific, just like selection of the right technology based on the size of the STP, here again for denitrification, you have to select the right denitrification technology based on the size of the STP and the limit of nitrogen here. We can never get 1 ppm nitrogen using any of these technologies. It becomes extremely difficult. We will have to go for this Barden-Foe process. So again, we have to use our knowledge, our skill in applying the knowledge which we have learned. This is the modified 5-stage Barden-Foe process, which I said. First is the anoxic anaerobic tank, followed by anoxic tank, aerobic tank, anoxic tank. This also does phosphorus removal, in fact. That is the reason the anaerobic tank was introduced. Secondary clarifier and effluent. And this is the recycle sludge, mixed liquor recycle, methanol addition, as I said. Methanol addition to introduce, give sufficient food for the denitrifying bacteria, and the aerobic tank to bring back the dissolved oxygen level so that the secondary clarifier works well. So this is the modified 5-stage Barden-Foe process which we used. And now for phosphorus control. Phosphorus is highly reactive, as we all know. Thus, it is never found in elementous phosphorus form. It is never found as phosphorus. It will be in the form of a phosphate. Found as organic and inorganic phosphate, oxidized form, in water, in soil, in sediments. Generic form of phosphate is the phosphate ion is PO4 3 times, gets into water bodies from multiple sources, which causes eutrophication. It comes through runoff from agriculture fields. It comes from leaching from the soil. When agricultural field, there is some amount of phosphorus which will get into the soil, and from the soil it can leach out into the water bodies. And thirdly, and mostly from sewage. Domestic sewage contains a lot of phosphorus. Typically, domestic sewage has about 4 to 5 ppm or even 6 ppm of phosphorus. You may think 4 to 5 ppm is very, very little, insignificant, but it is extremely significant. Even 1 ppm of phosphorus is extremely dangerous for these water bodies. It can cause eutrophication. So 1 ppm limit has been set not because it is best suited for the water bodies, but that is the limit of our technology. Aiming for anything less than 1 ppm is going to be extremely difficult in terms of achieving those standards in a treatment plant. And therefore, 1 ppm phosphorus is what is stated in most pollution control boards, and even in very, very advanced countries, like even in the state of Michigan. Michigan is surrounded by lakes, the state of Michigan in the USA. And therefore, Michigan state has very, very strict laws on nitrogen and phosphorus control. So that is the reason I selected the Michigan State's Environment Department's presentations on nitrogen and phosphorus. Extremely useful information from those presentations. Why phosphorus is both good and bad? Phosphorus is good. It's a vital element for all life, with phosphate compounds being an integral component of DNA, RNA, ATP, adenosine triphosphate, and is thus essential for all plant growth. This is the reason we apply phosphate, fertilizers like DAP, diammonium phosphate, we use in gardens and farms. It is bad when phosphates get into our water bodies. They promote unwanted plant growth, weeds leading to their destruction, upsetting delicate ecosystems such as lakes. This is why we need to remove phosphate in wastewater before we let it into the streams. Again, just as in the case of nitrogen, phosphorus is present in various forms. The simplest of phosphates present is in the form of orthophosphates, simplest and available for biological metabolism, as is There are polyphosphates which can be present. These are condensed phosphates consisting of multiple phosphate molecules. They contain salts or metals, but they hydrolyze very readily and revert to the orthophosphate state. So we do not have to do any special treatment to convert polyphosphates to orthophosphates. They readily hydrolyze to orthophosphate stage. Organophosphates, mainly from industrial wastewater, we don't see that in domestic sewage at all. These are esters of phosphoric acid and of minor importance in municipal wastewater. Organophosphates, as you know, are like pesticides and so forth. Organophosphates. So total phosphate is a combination of ortho, poly, and organophosphates. 1 plus 2 plus 3, typically 2 to 5 milligram per liter in sewage. Sometimes goes as high as 6 milligram per liter in domestic sewage. Phosphorus removal schemes. Removal can be either chemical or biological means. By chemical means, we use ferric chloride, aluminum sulfate. These are the typical standard coagulants in wastewater treatment, as you can recall. Even for the other textile industry, we use lime for plus ferric chloride, lime plus alum, things like that. Very versatile coagulants. Ferric chloride with phosphate forms ferrous phosphate. It precipitates as the metal phosphate, and therefore that's how you remove the phosphate from the wastewater. Similarly, using aluminum sulfate, aluminum phosphate is the precipitate which comes out of the wastewater. So typically chemical treatment for phosphorus removal. Biological treatment not covered in this presentation, does not make economic sense. We have done a detailed calculation of the costs, both the capital cost as well as the operating cost for different size of STP from 100 KLD to 5000 KLD, and up to 5000 KLD, we see it is economically optimal, more prudent to go for the chemical treatment rather than for the biological treatment. So again, the same rule applies. The technology, biological phosphate removal, comes in handy only beyond 5000 KLD and above. Coagulant dosing. So now we have selected chemical dosing, chemical precipitation of phosphate as the treatment technology to be used. Now the question arises, how much, what is the dosage? Where do you dose these chemicals? So there are various ways of dosing chemicals. There's something called pre-precipitation, co-precipitation, and post-precipitation, which I'll come to in the next slide. Correct dosage of these chemicals is required. 3 to 5 milligrams of ferric per milligram of phosphorus. Concentration, we have to also keep in mind that the concentration of phosphorus may vary through the day and with weather conditions, depending on the season as well. So it is important to dose the sufficient amount of phosphorus and not chemical, but not excess. Excess dosage will cause a lot of iron to accumulate in the wastewater. Phosphorus removal is most efficient in the pH range 5 to 7 for alum, 6.5 to 7.5 for ferric salt, since their precipitates will not readily return to solution. So these are very pH dependent, and therefore if you do not control the pH in this range, these are reversible reactions, and therefore the phosphate may come back into solution. So you have to be very careful and control the pH in the specified range only. So these are the points of addition of chemical. This is called pre-precipitation. This is a full-fledged treatment plant, which has a preliminary treatment, primary treatment, secondary settling, tertiary treatment, so forth. But in our extended we do not have a primary treatment. We don't have preliminary treatment. We don't do anything. It will be co-precipitation here at the front end of the aeration tank and at the back end of the aeration tank. This is what we do in all our extended plants. Front end of the aeration, this is very simple. Co-precipitation is what we use. But we could use pre-precipitation, because by just simple settling in a primary sedimentation stage, you can remove quite a bit of phosphorus here itself. So these are various techniques available for addition of chemical. So all it requires is a chemical preparation tank, LDP tank or an FRP tank, and a dosing pump. So you do not require any major permanent infrastructure to be built for phosphorus removal, unlike in the denitrification strategy, where you have to provide a new anoxic tank. Anoxic tank, typically about 1.5 to 2 hours retention time is required. So it's a fairly large tank, a large piece of infrastructure you have to retrofit and introduce in an existing STP or in a new STP. In this particular case, phosphorus removal, no such additional physical infrastructure is required. It is only providing a dosing tank, maybe a dosing pump. That's it. Overnight, we can implement a phosphorus removal strategy, unlike the denitrification stage. What are the chemicals used for phosphorus precipitation? Most common, ferric chloride, as I said, ferrous chloride, alum, and PAC, polyaluminum chloride. Polyaluminum chloride is a long chain alum, in fact. It's much more efficient, certainly. Ferric ion, Fe3, metal plus phosphate becomes metal phosphate, which precipitates ferric phosphate. Weight ratio. What is the weight ratio? Fe plus 3 to phosphorus, 1.8:1 is what is required. These are all very stoichiometric calculations, and therefore ferric chloride to phosphorus, typically 5.2:1 is what we require. So for every milligram of phosphorus, we have to add 5.2 milligram of ferric chloride. So the starting dosage, as we said, 20 to 25 milligrams, because we expect the phosphorus to be about 5 milligrams, between 2 to 5 milligrams. A good starting point for addition of ferric chloride will be about 20 to 25 milligrams per liter. But you could fine tune this later based on your actual experience, specific treatment plant site. As I said, it can be different. Phosphorus content also may be different depending on whether it's a residential complex or whether it's a mall or a hotel. So we have to actually study the phosphorus concentration, understand the phosphorus limitation and the limits to which it has to be treated. Similarly, for aluminum, alum dosage rates, weight ratio alum to phosphorus 0.87:1, alum to phosphorus therefore 9.6:1. Therefore, your alum requirement is higher than the ferric chloride requirement. Starting dosage therefore becomes 40 to 50 milligram per liter. Again, based on an average 5 milligram phosphorus, which we expect to be present in sewage. So what is the question here is, chemical or biological phosphorus treatment, what's right for us? Enhanced biological phosphorus removal, EBPR, is a separate presentation suitable for large municipal treatment plants. Our recommendation for small STPs less than 5 KLD is chemical phosphorus removal, best for CAPEX and OPEX. As I said, we have done a detailed study, Excel sheet study, based on the CAPEX, the size of the tank for a biological system as against the size of the chemical dosing system and the cost of the chemical and so forth. We have worked out it always is in favor of chemical treatment, phosphorus removal for up to 5,000 KLD. As a detailed calculation of tank and equipment, civil cost, chemical dosing cost for the two methods at different KLDs. Break-even for biological happens only for a very large KLD and not for decentralized urban STPs, as I said. So the key practical takeaways from this presentation: nitrogen control, anox tank followed by aerobic process, the extendation system is the most effective nitrogen control solution from both OPEX and CAPEX, treatment quality. We have implemented this in Phoenix Market City in Bangalore, and not only Phoenix Market City in Bangalore, about 5 or 6 different other locations, including residential complex, including for all the GE plants, the General Electric plants in Bangalore, and a few other residential complexes. And we continue to implement this denitrification now in all the other plants under our care. Even in regions outside of Karnataka, we strongly advise getting ready for an anox stage, as other states will follow and start enforcing nitrogen control. It is better to be prepared for nitrogen control rather than later trying to retrofit, because we have seen a lot of difficulty in retrofitting these anoxic tanks. Either we may not have sufficient space, or the layout is not friendly. It's not layout friendly to introduce a anoxic stage. So a lot of difficulties we face when we have to retrofit. You can well imagine trying to do something post thing which is already present is going to be extremely difficult. So in all the plants, we have introduced an anoxic tank. We may not introduce the mixed liquor recirculation. We may not implement denitrification, but the infrastructure is present. In case the pollution control board later, maybe 1 year from now, 2 years from now, starts enforcing denitrification, we are ready with that. Similarly, phosphorus control, we recommend chemical treatment as this is the best from capex opex. Chemical dosing only can be installed overnight, as I said. It doesn't call for a separate permanent infrastructure. Choose STP technology wisely for the long term. Next generation is the most modern. We have upgraded Phoenix, Bangalore, as I said, and Chennai to X generation with good results. This again for the Phoenix presentation. We are recycling several other Ecotech customers such as ITPL Bangalore, 3MLD. We recycle and reuse 93% from this ITPL out of 3MLD. Marriott Group, Hindustan Unilever, Pune, we all do X generation system. X generation, again, this goes back to the first presentation 2 days ago. X generation, many of these builders are now choosing the right technology. Since this was a presentation we gave to Phoenix malls, this is what we get. This is the quality of water we get in Phoenix Mall, which we are operating for the last 4 years. You can see in this mall, it's a 500 KLD STP. We also have a softener at the end of the treatment to generate soft water for use in their HVAC circuit, the cooling tower circuit. And we maintain a hardness of about 30 to 40 ppm, which is what is required in the soft water to be used. This is the quality of water. We have been running this for the last 4 years without a single day's disruption or interruption. This is the quality of water. And similar to the case in Chennai, this is the Velachery Phoenix Mall, Phoenix Market City. This is a 750 KLD STP, and we recycle and reuse nearly 600 KLD every day. Again, huge HVAC requirement. So this is the certificate or whatever testimonial we received from the senior director who is in charge of all the malls, Phoenix malls in South India. And now Phoenix is setting up a very huge mall in Bangalore, the second big mall in Bangalore, 1,100 KLD. We have designed a ETP for that, acceleration again, with denitrification. Denitrification already included in this treatment plant. So that is the presentation on nitrogen and phosphorus removal. Just an introduction. We can get into more detail. You can go to the Michigan State website. They have a lot of good information on nitrogen and phosphorus control. Some of the best presentations on nitrogen and phosphorus. So if you go to many of these sites, you will get a lot of information, but you have to be selective in understanding which are useful, which are not useful, which are more academic, which are more practical. And I found this Michigan State Department of Environment, many of their operator training manuals and other things, extremely practical. So we have borrowed many of these things from that. Even our STP operator training programs syllabus, we conduct operator training programs for STP operators. It's a 2-week to 20 days program with theory, with practice, with site visits and other things. We have developed the curriculum, and as I said, we have conducted 7 batches already. And this is under the Skill India program, and we issue certificates recognized by all government bodies. So any of you interested, again, I would request you to catch up or connect with Dinesh, who can organize a visit, STP visit to Phoenix Mall in Velachery. So thank you all. Thank you for your patient listening. I will.
Thank you very much.
Any questions on nutrient control?
Any questions by the participants? Sir is willing to take some questions. I think today Sir was a little on the faster side and has given us a lot of information. Anyway, we'll be sharing the material with you. So I think do you have any questions, participants?
Let me share with you also that we have, as I said, we have introduced denitrification now in about 6 or 8 of our plants, and we are getting extremely good results. Nitrogen definitely less than 10 milligram. So it calls for a detailed analysis. As you know, the typical aerobic biological reaction itself removes some nitrogen and phosphorus in the ratio of 100:5:1. So only the residual nitrogen. Supposing you have 200 BOD. If BOD to nitrogen to phosphorus ratio is 200, 100:5:1, 10 milligrams is taken up by the bacteria itself, the carbon eating bacteria itself, and therefore only the remaining nitrogen has to be removed by the denitrifiers. So we have to do a lot of good analysis and calculation and computation before you design your mixed liquor recirculation rate. So I have a small additional presentation on that itself, because MLR recycle is very, very energy intensive. So you have to optimize that energy consumption, and so you take into account all the advantages that the aerobic treatment plant provides, the externalization. So there is a contiguous nitrogen removal as you remove the BOD itself, and therefore only the remaining nitrogen has to be controlled in the anox denitrification stage.
இது இங்கயா அங்க இருக்காது நீ தானே ஆனே Participants, do you have any questions? No questions from the participants. Then I think, sir, we thank you once again for having spent so much of your valuable time and given us a very interesting and informative talk. A talk loaded with a lot of information. I presume it should be useful for all the faculties that who are attending the program. And thank you once again, sir.
Yeah, thank you, Dr. Lima, and thank you all participants for your patient listening. So Dr. Lima will share you the PPTs. I have already shared with her. And if you have any questions, you can always get back to us. We are always available for help, anything. Not only on the 2 presentations which you have given, any other things which we believe we can help or we have knowledge, we will be happy to share. Thank you all.
I think I had muted them, so I'm sorry. Is there anybody who would like to ask any questions? Now I have unmuted all of you. Because in between, during sir's talk, there was some background conversation, so I had to mute you.
Anand sir.
Yeah.
Can we use the solar energy or for the purification of this water or this sludge operating system?
I think you could do that. Yeah, in fact, we are trying to at least start introducing this. We are trying to tie up with some solar cell suppliers so that residential complexes, we can bundle it. Both energy and water are the 2 key things which we should ensure that the citizens of this country are not deprived of. So solar energy and water from treated STP water, recycle and reuse. These are 2 things we are trying to bundle. We are trying to tie up with some other similar companies in the solar energy field, and we are trying to do that. Yeah, bulk of the energy requirement in a treatment plant can be met by solar energy, especially in large complexes, residential, commercial complexes with a large rooftop area.
Anand sir, in one slide you told about that automatically controlled. It means you use some artificial intelligence and these like systems?
No, we have not gone to that stage yet.
Okay.
What we said is we put in this real-time monitoring systems. Right now, we are only monitoring the plant. We are not controlling the operation of the plant yet.
Okay. So, is it sensor-based system, sir?
Yeah, it is sensor-based. Typically, the CPCB has mandated. It is now mandated that all the STPs in India should be monitored by these real-time monitoring systems. We have to monitor pH, suspended solids, BOD, COD, and the flow, the treated quantity. So how BOD and COD is monitored is not a direct measurement of BOD and COD. It's not possible online. So what is typically the technique used is we measure either the suspended solids and turbidity or turbidity nephelometric methods, and then use a regression equation to get to the BOD and COD, because there's a direct correlation between turbidity of treated sewage and the BOD and COD. So depending on the clarity and the color and other things, you can tie it up with to the COD and BOD levels. And the regression equation is fairly good, statistically significant. It is statistically acceptable. And in fact, we have developed this technology with IIT Madras. Over 80 samples, we have developed the regression based on the turbidity of the treated water. So once you measure turbidity and suspended solids, which is very easy to measure rather than direct BOD and COD, then you use the correlation or the regression equation and get to the COD. That is perfectly acceptable. That's what everybody does world over. Either you use nephelometric technique, or you could use the very sophisticated UV visible spectrophotometer, again to measure suspended solids, and then tie it up with to the BOD and COD. So for the domestic sewage, it is fairly very simple, straightforward, because domestic sewage, the characteristic remains the same. Whether the characteristic remains the same, whether you are in Bombay, Bangalore, Chennai, Delhi, wherever, or even America, Europe. Domestic sewage consists of only carbohydrates, proteins, and fats. There are no other chemicals or components except maybe again the nitrogen and phosphorus. Unlike industrial wastewater. Industrial wastewater is a totally different kind of beast. That matrix is totally different, and as I said, from hour to hour, to minute, it will change, and therefore you may have to go for these sophisticated, very sophisticated instrumentation and correlation techniques, and constantly also recalibrate it, because it doesn't remain the same from season to season as well. For instance, in a bulk drug industry, they do campaign basis. They'll do production. They will make some drug today. The next month, it will be a totally different drug using totally different set of chemicals, or hundreds of chemicals components will be there. So it becomes extremely difficult. But what we have developed is specifically for domestic sewage, very simple, using nephelometric technique. We don't need these sophisticated imported UV vis spectrophotometers, and very cost effective. It's 1/10 the cost of these imported instrumentation, and easy to maintain. A turbidity meter is very easy to calibrate and maintain rather than the UV vis spectrophotometer. I hope that answers your questions.
Any other questions by the participants?
Thank you, Anand sir.
Thank you very much, sir, for spending more than 4 hours with us and the participants, and giving us a lot of information about STPs and ETPs. And as chemical engineers, I think we are more interested in ETPs, and you have given an insight that we can't have one ETP for one type of ETP for all the industries. We have to look into what is the effluent and then work accordingly. So thank you very much, sir, for your good talk. Very highly informative. Thank you once again.
Right, Dr. Lima. Thank you again. Thank you all for participating and patiently listening to this. As I said, we are always available to you.